All right, so hi everybody. So today we get our third lecture on magnetism, and what I want to do today is show you a little bit more about some of the equations of magnetism. Okay, I'll remind you a little bit about some ideas in magnetic forces, and show you another example of Ampere's law. How do you solve if you got, say, a non-uniform current density and so on. And then I want to spend the rest of the time talking about this vector A, this vector potential, which is kind of like the voltage for magnetism. I want to give you a little bit more of a feel for this thing. And get a little bit more practice and show you how you can think about this. But it turns out, actually, we've already done a lot of hard work, because it turns out that the equations that describe the vector potential can be made to be precisely the same as the equations for the regular potential, the electric potential, the voltage. And so all the work that we did for solving for the voltage can also be applied to the vector potential. The only difference being the vector potential is a vector, whereas the electric potential is a scalar. It's often called the scalar potential. And so that means that you only have one of the voltages, but you got three components to the vector. So you might have to do the same integral 3 times, sort of thing. Okay? And so I want to spend some time talking about that. Okay? Next time I hope to have one of these special lectures on magnetism of matter, but then after that we're going to go on to discuss what happens when things start changing with time. And so everything today, again, will be static, but after the special lecture, we'll go on and actually talk about the full time-dependent situation. Then we start getting into very interesting things, and we start seeing why it's electromagnetism and not two separate things. Okay? So as always, we start with our slides here showing the equations, the Maxwell equations, and we've kind of put a whole bunch of these things together now. We kind of get a very good idea about these things. In fact, we have most of this. We have, just sparkles for emphasis, we have this one, okay? Gauss's law for electricity. We have Gauss's law for magnetism. We do not have this next one. Okay, this one we don't know yet. That one is going to wait. Sorry, going to wait a couple of lectures. Okay, this one here, we've got some of it. Okay, we don't have this last part just yet, but we do have the Lorentz force law. We've got part of the electric field, and we also have the magnetic field. Okay. So some of these parts, notice all the parts that we don't have are the parts that involve time derivatives. We've been keeping everything fixed in time now, time independent, everything static, up until today, and including today and the next lecture. But very soon we're going to look and see what happens when things do change with time. All right, but we've already got a whole bunch of this stuff. And so specifically what I want to talk about today is the magnetic field and these rules here. Okay? These first two things here are Gauss's law for the magnetic field. Okay? This is the integral form, and then this is the differential form. And we've talked about these things. These things say that magnetic fields do not diverge, they do not spread out, they form closed loops. Okay? And so that's equivalent to saying that there is no magnetic monopoles, that you don't have individual north poles and south poles of a magnet. Cut a magnet in half, you don't get a north and a south. You get a north and a south and another north and a south. All right? That's what these equations say. Okay? Based on, and again, that's an experimental question, and so experimentally, so far, we do not see any magnetic monopoles. Again, it would not be hard to change these things up to make them look a little bit more like Gauss's law for electricity, but we just haven't had an experimental reason to yet, although there are plenty of theoretical reasons to do so. Okay? Now, based on Gauss's law here, okay, and again, these laws here are exact. Okay? They are exactly true. And that means that even when things do start changing with time, they are also true. Okay? But again, these are constraints, Gauss's laws. It's a constraint, meaning that any magnetic field that you write down has to be consistent with that. It has to have zero net divergence. Okay? It has to have no net flux. But again, that's not very unique, okay? It's not very specifying in terms of the magnetic field. Any magnetic field has to satisfy this property. So you can't use this by itself to determine what the magnetic field is, okay? You need to use another law like Ampere's law in order to specify that, okay? However, based on this, okay, based on the fact that the divergence of the magnetic field is always zero, this means that you can always write B as the curl of some other vector because del dot del cross A is identically equal to zero. It's always equal to zero no matter what the A is. And so if you have a vector that always has a zero divergence, then that means that you can replace that vector by the curl of some other vector. Okay, and so that's another way of writing this. And this vector A is called the vector potential. And that's the case that I want to spend most of today discussing, but not all of it. I want to show you a couple more examples of a couple of other things first. Right? So this comes from this. Notice, this is very much like the fact that since E... Let me just start in the... Well, since E... Okay, just writing this in some other case. Because we can write in the time-independent case, E is minus gradient to the voltage, this implies that the curl of E is zero. And so if you say that the curl of E is zero, that E can always be written as minus the gradient of some vector. All right? I'm sorry, of some scalar. Right? And this comes from the fact that the curl of the gradient of something is always equal to zero. And again, there's sort of geometric reasons for this. Remember, the gradient tells you the direction you had to get from point A to point B as fast as possible, and the curl tells you how much something spins around. Well, if you're going from point A to point B as fast as possible, you're not spinning around. Same thing here. Okay? If you're spinning around, you're not spreading out. Right? And so these are the ideas. So I want to spend a lot of time talking about this and giving you some more intuition about the vector potential and so on. But let me do a couple of other examples first. Okay. First example I want to do is I want to remind you about magnetic forces. Okay. Case of magnetic forces. Remember that in general, if you have an electric field and a magnetic field, an electric field E and a magnetic field B, then if you got a charge in that electric and magnetic field, then the force acting on that is this, okay? Q times E plus V cross B. The Q times E is the electric field, electric force part, and then Q times V cross B is the magnetic force part. And V here is the velocity of the charge. And so you remember that the magnetic force is Q times V cross B. So the magnetic force is at right angles to both the velocity of the charge and the direction of the magnetic field. So if you've got something where V points this way and B points in that direction, then the force, magnetic force, is at right angles to both of them. Okay. All right. And if V and B are heading in the same direction, then the cross product is zero. There isn't any magnetic force. All right. So here's an interesting example. Suppose you've got two wires carrying current, say, in the same direction. Both of these things produce a magnetic field. The magnetic field, you know, circles around them. And so suppose that red is going to represent the magnetic field here. So from the magnetic field, from the top one, it's going to circle around, and it comes out of the page up here of the screen and goes into the screen down there. So it circles around like this. Okay? How do I know that? From the right-hand roll. Again, you imagine grabbing the wire with your thumb pointing in the direction of the current, and then your fingers curl around in the direction of the field. Okay? Same thing from the bottom. Comes out of the board here, okay? Goes into the page down there. Okay? And just to remind you, the magnetic field of this long straight wire is mu naught I over 2 pi r, okay? Where r is the distance away that you are. So here's the thing. You've got these charges which are moving around in these wires. And so the top wire produces a magnetic field that acts into the screen at the position of the bottom wire. And the bottom wire produces a magnetic field at the position of the top wire that points out of the screen. Okay? So this is field from top wire and this is field from bottom wire. All right. But you've also got charges which are moving along in there. And so if you picture these charges, which we'll take to be positive, if you picture these charges, okay, these charges are heading in this direction, so that's the direction of their velocity. These charges are heading in that direction, that's the direction of their velocity. And so there's going to be a magnetic force acting on these things. And the magnetic force is going to be what? Well, V cross B from the bottom one, V is to the left, B is in. There's going to be a magnetic force pointing up on this wire. How about from the top? Well, V points to the right, B points out. There's going to be a magnetic force pointing down. And so when you got two wires that have current which is moving parallel to each other, these wires attract each other. They move towards each other. If the currents are traveling in opposite directions, they repel each other. I want to know, what's the force acting between these wires? More specifically, since these are infinite wires, what's the force per unit length? Okay. What's the force between two 1 meter sections of these wires? How do I figure it out? Well, I go back here. I know that the force acting on these things. Let me take a little tiny piece here, a little tiny dq, okay, and look at a little bit of charge. The little bit of force between these things should be the little bit of charge times V times B. Okay? And there's no sign here because everything's in 90 degrees. V and B are perpendicular to each other. And so you get this. Now, this is the same thing as dq times dx dt times b. And that's just because velocity is derivative with respect to time. Now again, I can write this because dx and dq are moving in the same direction. This is the same as dq dt times dx times b. But remember, after all, what dq dt is. This says that df is equal to the current times dx times b. And so therefore, if you integrate this thing along a certain, well, if you like, this means that df dx is equal to I times b. Okay? So the current in one wire, and this is our force per length, okay? The current in one wire times the magnetic field that that same wire feels. And so just to actually get a number for this thing, okay, let me take this expression, so my force per unit length, okay, which is my df dx, I'm just sort of extending it out, is the current times B. But here's the B. And so suppose that the separation between these things, we call it D, then this should be, well, if it's the same, well, let's call this I1 and I2, just for generalization. This will be I1, I2 over 2, mu naught pi d. Okay? So, that's the force per unit length. Not so bad. Nothing to it. All right. So, the other thing that I want to discuss is show you another example of Ampere's law and think about it a little bit more. Okay, so Ampere's law you remember, let's say the integral form. Let me write it. Integral b dot ds is equal to mu naught times I through. Okay? And so this thing says that if you've got some currents which are moving along, okay, some amount of current, and you imagine drawing a little loop around these things, then the magnetic field integrated around that loop depends only on how much current passes through the loop. Okay, that's the idea. This also, well, I'll say more about the also in a minute. All right, so let me do another example of this. Okay, let's suppose that we have Suppose we got a wire, a thick wire, with current density, let's say J of R. Okay. J of R, what does this mean? Well, remember what this J of R is. This J here is defined such that the total current is integral J of R dot dA. If you got some wire here, J is the current per unit area, such that if you integrate over the width of this wire here, okay, you get the total current in that wire. So that's the idea. And so here's the idea. Suppose that I got a situation here where I've got a thick wire here, let's say of radius A, and I want to know what's the magnetic field. Okay, well that's easy, but what's the magnetic field inside and outside? Okay, the magnetic field outside is easy. It's just B is mu naught I over 2 pi R, where R is the distance away that I go. Okay, so if I'm out here, that's the field. Why? Well, if I draw my little Gaussian loop, it encloses all of the current. And this is exactly the same thing as we saw for Gauss's law for electricity. If you're outside the electric ball, then you just see Coulomb's law. But now, what if you're inside? Now suppose I come out here a distance R. Well, now in that region, you don't enclose the entire current, only a part of it. How do you do that? Well, I think you might be able to guess. Just like we did for Q enclosed was integral of the charge density over the volume, here we integrate I through should just be integral J dot dA for the enclosed loop. In other words, I figure out how much current actually passes through that part of this loop. Okay, what fraction of it? And so let me redraw this. So here's the idea. Here's my full wire carrying this current density, J, which again is my current per area. And now I come out here, a certain distance R, and I draw my Amperian loop, and I want to figure out how much current is passing through that loop. Okay? Well, the way that I can do it is by thinking about this area here as made up of a bunch of little rings. Okay? Rings of radius R and a little thickness here, dr. Then the little bit of current that passes through that little bit of area here, okay, this little thickness dr, the little bit of current that passes through there, this little di, should be equal to the current per area times the little dA. And the little dA, okay, because it's all in the same direction. dA points one way and the current heads the same way. This should be dA should be just the area of this little strip, which if you imagine slicing this strip and stretching it out, it should be the length of that, 2 pi r times dr. And so di should be equal to 2 pi r j of r dr. This assumes that the current doesn't change with angle. This only assumes that the current changes from direction, okay, by radial direction, how far you go out. And that's the case that I'm going to consider. If you wanted to include, this is just to write it, if you wanted to include j of r and theta, okay, dA, then your dA in this case would be r dr d theta, okay, or d phi if you want to call it that, whatever it is. But again, we won't worry about that so much. Okay, you'd have to integrate over theta as well. Okay? And so this tells me that the current then would be integral, 2 pi r j of r dr from 0 out to whatever r you're looking at. Okay, this would be your I through. Okay. And so that's a general case. Okay, and again, this might remind you a little bit of Q enclosed is equal to integral 4 pi r squared dr times the rho of r. Okay, it's the same sort of idea. A little bit different because you're integrating over an area versus volume, but it's the same idea. Okay, so with this in mind, let's do an example. Okay, so as an example, suppose that you got a current density I don't know, J of R, just making something up, is some, let me write it this way, J0 over R times R. Okay, so it depends proportional to the first power of the distance. And R is the radius of the wire. Okay, so the radius of the wire here is R. Such that the total current on this thing is I. But this is how it's spread out. You got no current in the very center, and then it gets bigger and bigger towards the surface. All right? So, question A. What's J0 in terms of the current? And then B, what's B inside? In other words, for regions from 0 out to R. All right. I'm not going to ask what's B outside because I already know that. B outside is just this. Okay? So how do I figure it out? Well, again, this is very much like the Gauss's law problem we did, where I asked, okay, the charge density is some constant times R to the third power. What's that constant? It's the same thing here. If I integrate over the whole wire, then I through is equal to just I. It's the whole thing. So in other words, if I integrate I is equal to 2 pi integral 0 out to R, J of R, R dr, then I should get the entire current. If I integrate out to some intermediate distance, okay, if I just go out this far, then I just get how much current goes through that little spot. Okay, and so first thing I'm going to do is work this out. And so this becomes 2 pi J0 over R times, again, R from the J, okay, and just you check this, okay? I end up getting R squared over 2 when I do that integral. You can see where it comes from, okay? Again, I just don't want to take the time to do the steps. And so what do we get? We get pi J0 R. And so that tells me that J0 is equal to I over pi R. Okay. Yeah. Notice, this tells you that your J of R is equal to I over pi R squared times R, which is kind of what you might have expected. Wait, something's wrong. I am so sorry. This is why it's bad to go too fast. That was wrong. The units didn't work. Okay? That's not R squared over 2, it's R cubed over 3. And so this is 2/3 J naught R squared. Okay? And so that tells me, and this is equal to I, and so J naught should be equal to 3I over 2 pi R squared. Okay? And so that gives me my J of R. Okay. All right, so that's part A. Now part B, what do I do? B inside. Well, again, I've got this thing here. I got my wire out here to radius R, and now I just I come out here to some distance little r, and I take my Amperian loop. And I want to use Ampere's law. B dot ds should be equal to mu naught I through. Okay, how much current passes just through that region? All right. Now, I know that the magnetic field, because of the symmetry, if I can rotate this wire around and still look the same, that means the magnetic field can't depend on the angle. And so the magnetic field has to be the same everywhere along this loop. And so because of that, and if I step along this loop, this side here just becomes integral B ds if I'm walking in the same direction, and that's B integral ds because B is constant on this loop, and so that's just B times the length of that loop, which is B times 2 pi R. Okay? So again, if you pick a good loop, it's always the magnetic field times the length of that loop. Just like in Gauss's law, it's the field times the area through which that field is passing. All right, so now I just got to figure out I through. Okay? Well, I through is easy. Okay? This is just integral 2 pi integral j of r times r dr from 0 out to r, this radius here. Okay, if it bothers you, call this j prime, r prime, d, r prime, and so on. All right? And so this gives you 2 pi j0 over r, I'll plug in the j0 in a second, times little r cubed over 3. And with that in mind, this tells me that my I through, writing it up here, after I plug in for j0, should be I times little r cubed over big R cubed. Okay, when I plug in for this thing. All right, all the 3/2 and all that kind of stuff cancel. Notice, when little r equals 0, I get no current. When little r equals big R, I get all the current. So again, it's always nice to check these answers. And so this should be equal to mu naught times I through. And so this tells me that B inside is equal to mu naught I over 2 pi r cubed r squared. Okay, and it circles around. Notice, when little r equals big R, B inside at R is equal to B outside at R. Okay, so see how it goes? So nothing to it. Not so bad. All right, so you can try it for other situations as well. Okay, but I just wanted to show you another example of that kind of thing. Okay, all right, now, another way of writing Ampere's law is the differential form. Okay? By Stokes' theorem, which we talked about last time and have talked about before, integral b dot ds is the same as integral del cross b dot dA. And this is supposed to be equal to mu naught times I through. But we've just seen that this is the same as integral mu naught j dot dA. And so if these two things, these two integrals are supposed to be equal to each other, no matter what our area is, that tells us that the integrands have to be equal to each other. And so this is another way of writing Ampere's law. And this is very nice. If you know what B is, you can use that to figure out what J is, and so on. Okay? And so you just have to work out the curl. And the curl can be sort of this nasty sort of thing. Depends on which units you want to, or which coordinate system you want to use. If you want to use Cartesian coordinates, it's one thing. If you want to use cylindrical coordinates or spherical coordinates, it's something else. Okay, you've got all these things written down in that handy electrodynamics information sheet. Okay, so I do encourage you to use that one. Okay, and so this is nice. Okay, this is a good form if you know what B is and you want to figure out what J is. Okay, that's very much like the this form here of the electric field, Gauss's law. This is nice if you know what E is and you want to figure out what the charge density is. Okay, it's the same sort of thing. Now, so let me kind of spend a little time looking at this. There's an interesting and useful identity that we talked about for vectors. If you take the curl of some vector, okay, so f here is just some vector, it turns out to be the gradient of del dot f minus del squared of f. Okay, this is an identity. Again, it's in that handy electrodynamics information sheet. So you've always got it there. You can try proving this. In fact, it's nice to try to sort of sit down and actually prove it and see that it comes out. But this is something that we're going to use a couple of times today, so I sort of wanted to mention it. Okay, and by mentioning this, I want to apply that to this. Okay, and so when you write this thing down. Let me apply this to my Ampere's law. This is gradient of del dot B minus del squared of B, and this should be equal to mu naught del cross J. Now the thing is, from Gauss's law, this term is 0. Del dot B equals 0. And so I just got that. And so my Ampere's law is equivalent to saying that del squared, the Laplacian of B, is minus mu naught del cross J. This is one of these Poisson equations that we've been talking about. What was a Poisson equation? Well, you remember, in the case of electricity, okay, I've got that del dot E is rho over epsilon naught, and that E is minus the gradient of V. So taking the divergence of this, I get del squared V is minus rho over epsilon naught. And so that's another Poisson equation. And so what does that tell us? Okay? Well, I remember the solution to this, okay, which I've written a bunch of times. V at R is equal to 1 over 4 pi epsilon naught integral rho of R prime d3r prime over R, where R vector is R minus R prime. So again, remember the whole idea. Here's your origin. You want the field over here, okay? And here's your charge distribution over here. You go to some little dq prime, and this is your vector R prime. And this R is R minus R prime. So you take the charge distribution, you break it up into a whole bunch of little pieces, dq prime, which is rho of R prime, d3r prime. This d3r prime just means, the little volume. And you integrate over this. And so that's the solution. But notice, we've got exactly the same Poisson equation. We're just replacing one thing with another. And so that tells me I can write down right away what my solution for B is. It's going to be equal to mu naught over 4 pi. Okay, again, just making substitutions. Del, let me write this way, del prime cross J of R prime, d3R prime over R. Okay, it's exactly the same thing. What does this del prime mean? Well, it means derivative with respect to the primed coordinates. Okay, so this means, for instance, del prime of f of x prime, y prime, z prime just means take derivative with respect to x prime, I hat prime, plus derivative of y hat prime, j hat prime, and so on. Remember, you're integrating over the prime coordinates, which is this bunch of stuff over here, okay? We're not going to do too much with this solution, but it's nice to be able to write it down very, very quickly, okay? And so that means that stuff that we've done for voltages also applies here. Okay. So again, we're not going to do much with this. In fact, you can prove, and I'm not going to do it, it's just more algebra than I want to spend time on. You can prove that this is actually the Biot-Savart law. Okay? This is equivalent to the Biot-Savart law. So that's another way of thinking about it. So the Ampere's law gives you the Biot-Savart law. And remember, that's the idea, that the Maxwell equations are really all there is to electricity and magnetism. You can get every other equation from them. Okay. All right. So now, I want to talk about this vector potential. Okay? Because it looks a little new, and it looks a little different, and it might be a little bit of something that you got to get the hang of, but actually it's not bad at all, because we've already done the work when we talked about these voltages. You'll see what I mean. Okay? So where does this vector potential come from? From Gauss's law for B. Okay? This says that the divergence of the magnetic field is always equal to 0. Okay? Every situation, all the time. Because the divergence is always equal to 0, because the divergence of the curl of a vector is always equal to 0, this implies that B can be written as the curl of some other vector. Okay? And this other vector here, okay, is a vector, and it's what's called the vector potential. Okay? And as we'll see, it's like the voltage for magnetism. Okay? And so it's very much like the V here. The V for electricity is like the A for magnetism. However, you notice they're different. E is minus the gradient of some scalar. B is the curl of some vector. Okay, and so they're a little bit different. But they will end up satisfying the same equations. And in fact, we'll use that idea to get the vector potential in nice situations very quickly. All right? Now, there's something very interesting about this. Okay? Think back to the voltage. Okay? You know that E is minus the gradient of the voltage. Okay? But this says that V is not unique. Okay? V is not unique. Why? Well, suppose I take V and I change it to some V prime. Prime here just means something different. Let me not use prime. That makes you think derivatives. V twiddle. Okay, this twiddle. Just something different. Which is my old V plus a constant. Okay? So I just shift my voltage by a constant. In that case, my E goes to the E twiddle, which is minus the gradient of V twiddle. Okay? So I'm just shifting everything through. And this is minus the gradient of V plus constant, which is minus gradient of V plus 0. Right? Well, the derivative of a constant is always 0. And so this is equal to minus, plus E. So in other words, shifting V by a constant doesn't affect E. We say that the electric field is invariant under this shifting constant. And this means we can choose the constant however we like. And in fact, we did that. Every time we figured out what the voltage was, we would figure out what the change in voltage was between two different points. And I would always say, voltage relative to what? Relative to infinity. I was always choosing my constant in such a way that I could make my voltage, well, whatever I wanted it to be. Because only differences in voltage matter. Okay? And so you can always choose this constant. You can always add any constant you want to the voltage and have it not change the physics. And by change the physics, I mean not change the electric field. Okay? And so that's very, very handy. Okay? But again, you've known about this since Physics 101. Okay? If you're throwing a ball into the air, you can count your potential energy from your feet, from your hand, from the Andromeda galaxy. It doesn't make any difference. Okay? Do we have something similar for A? Yes, we do. Okay? Again, what about for A? Okay? Sure, we can always shift A. Yep. We can do two things. One, shift A goes to some A twiddle. And again, the twiddle just means something different, which is A plus some constant vector, V, which is a constant. Okay? Well, the curl of a constant, well, in this case, B will go to, in the same way, B twiddle, which is del cross A twiddle. And that's del cross A plus del cross V. But the curl of a constant, remember, curl is a whole bunch of derivatives. This is 0, and so that's B. Okay? So yeah, shifting A by a constant makes no difference. So shifting A by a constant doesn't make any difference, in the same way that shifting the electric potential by a constant also makes no difference. Okay, but can we do anything else? Well, yeah. Suppose we shift A goes to this A twiddle, which is my old A, plus something else, plus the gradient of some scalar. Okay, so lambda here is just some scalar function. And what is that function? Well, whatever I want it to be. All that I know is it's just some scalar function, and I'm adding to A the gradient of some scalar. What does that do? Well, all right, well, what's going to happen? Well, then B is going to shift under this thing to my B twiddle, which is what? Del cross A twiddle, which is del cross A plus del cross del lambda. Well, this first part here, that's just my B. The curl of the gradient. Well, remember what that is. The curl of the gradient. Did I write it somewhere? Just looking. Well, right here. Curl of the gradient of anything is always 0. And so, because the curl of a gradient is 0, this piece also goes to 0. And so this tells me that B twiddle is the same as B. So in other words, shifting A by the gradient of some function makes no difference. Okay? Makes no difference either. And so we've got kind of a stronger sort of symmetry group, if you want to call it something fancy. We've got sort of a stronger bunch of things that we can do for A than we can for the voltage. Okay? And so that's kind of nice. So you're always able to sort of shift A by adding the gradient of some scalar, and it doesn't make any difference. This lets you do some interesting things. Okay? For instance, suppose that you have some vector. Okay? Suppose that you got some vector. And suppose you want to enforce a certain constraint on this thing. Suppose you want suppose you want del dot A equals 0. Suppose you want to make A to have 0 divergence. Why would you want to do that? Well, sometimes it might make the equations look simpler. We'll see this in a little bit. Suppose you want to do that. How can you do that? You say, well, isn't this some physical thing? Not really. Why? Look at this. Okay? Suppose you want to choose this. Okay, how can you do it? Well, here's an idea. Imagine you start with some A twiddle. Okay, so you're starting with some vector. This is the vector potential. This is the one you're beginning with. Such that, okay, del dot A twiddle, this thing here is not equal to 0. Okay, let's call it, I don't know, some f. Okay, so this is some f of x, y, and z. So it's some function. Okay, so in other words, you're starting off with some vector potential, and the divergence of that vector potential that you get, say, by solving equations, comes out to be not 0. Comes out to be some function. But you really want this thing to have 0 divergence. Why? Because it makes the equation so much nicer. Is there any way you can get away with it? Yes. Remember, if I shift, okay, my A twiddle, I can write this as A, say, minus the gradient of lambda. I'm just kind of going backwards here. I can write it this way. Then in this case, notice my del dot A twiddle will be del dot A minus del dot del, well, this is del squared lambda. But this is f. Okay. So now I never said what the lambda was. This is completely up to me. suppose I choose lambda so that del squared lambda is equal to minus f. Suppose I just choose that. Okay, can I do that? Well, yeah, sure. I never said what lambda was. If I choose this, and then this tells me, well, hey, this is my Poisson equation yet again. So my lambda of r is my 1 over 4 pi integral f of r prime d3 r prime over my r. I know this solution. If I choose lambda to be this, then these two terms cancel, and I get that del dot A is equal to 0. And so I've got that constraint. I've got that condition that I want. Okay? Have I changed any physics? No, because I don't change the physics. I don't change the fields when I make these substitutions, when I make these transformations. And so this is nice. Okay? And so you can always do that. Nobody ever sort of actually writes down what it is that you choose. You just say, I'm going to choose A so that this is true. But you can always do that. Okay? And so this is one nice choice. Okay? There's another nice choice which shows up. This process, okay, and I'm just telling you names for these things, so don't get scared. This is what's called a gauge transformation. Okay? A gauge transformation is this thing, is changing A by adding the scalar, the gradient of a scalar. It's called making a gauge transformation. And choosing a value for lambda, this is called a gauge choice. Okay? And this here, okay, this particular one, this is what's called the Coulomb gauge. Okay? So by choosing the Coulomb gauge, in other words, picking this for our lambda, we can make this choice for the divergence of A. Okay? So again, a little bit of fancy stuff here, but I hope the idea is kind of clear. The whole idea is that you don't change the physics if you shift A by some gradient. But you never said what that gradient was. You're free to choose what that gradient is. And in particular, you're free to choose it in such a way that you can enforce certain conditions on A. All right? And that's something that we're going to want to do. Why? Well, let me go back to my equation here. B is del cross A. And remember that del cross B is equal to mu naught times J. Well, let me take the curl of B. Let me take the curl of B. Okay, so I can take the curl of B and then plug it in to my Ampere's law. So the curl of B, is this, okay, because this is my B. And so remember this identity that I wrote down back here somewhere, this one here. Okay. This is the same as del of del dot A minus del squared A, and this should be equal to mu naught times J. Now, if I make that Coulomb gauge choice, okay, if I choose to work in the Coulomb gauge, this is 0. And so now you notice my equation, del squared A equals minus mu naught J, which once again is the Poisson equation. It's really 3 Poisson equations. It's one for x, one for y, and one for z components of A. Okay? And so having those gauge transformation ideas makes this thing very, very, very simple. And it's very simple because we've solved this already. Okay? Once again, I know my solution. A of r is equal to mu naught over 4 pi integral j of r prime d3 r prime over r. Okay? So it's just like the voltage. Okay? In fact, I'm going to make that more explicit. But just to make sure you know what I'm talking about, remember, A is a vector. It's got some x component I hat plus some y component j hat plus some z component k hat. Similarly, j is also a vector. It's got some jx I hat plus some jy j hat plus some jz k hat. And so what Poisson's equation is here, the expression here for A, this is equivalent to 3 equations. Okay? This is the same as saying that AX of R is equal to mu naught over 4 pi integral JX of R prime D3 R prime over R. AY of R is equal to mu naught over 4 pi integral JY of R prime D3R prime over R, and so on for Z. Okay? So del squared A is equal to minus mu naught J is really 3 equations. Okay? All right. But that means that we know all of these solutions. Okay? Because what this means, you compare. Okay? Electrostatics to magnetostatics. Okay? By magnetostatics, I mean, again, all time derivatives are set equal to 0. Here, you've got del squared V is minus rho over epsilon naught. And so the solution of this, V of R prime, is 1 over 4 pi epsilon naught integral rho of R prime D3 R prime over R. Here, del squared A is minus mu naught J. And so the solutions here, A of R, again, it's 3 equations, not R prime, A of R, is 1 over 4 pi mu naught integral J of R prime D3 R prime all over R. So notice, this is exactly the same thing as taking my solutions for the voltage and then replacing 1 over epsilon, well, V goes to A. Okay. Rho goes to J, and 1 over epsilon naught goes to mu naught. Okay? And so we've got these nice substitutions here. Okay? We've got very nice substitutions here, which tell us that everything that we did for learning about voltages, all of those situations where we learned about voltages, we can also use these to figure out the vector potential. Okay, so we don't have to go through all the same work again. We've already done it. And that's nice. The same, this is important. Okay? The same equations have the same solutions. Okay? The same equations have the same solutions. And so the fact that we learned so much about voltages already means that we've now learned so much about magnetic voltages, okay, vector potentials. Okay? So, again, let me just sort of mention something about this, then we will see an example. Notice, this thing says that A is parallel to J. Okay? So the magnetic vector potential points in the same direction as the current. Okay? You can also write this in a slightly different way. Okay, so let me write this. A of R is equal to, again, just rewriting it, mu naught over 4 pi integral J of R prime D3R prime all over R. Now suppose that this is on a wire. Okay? And here's your wire. Your J heads in this direction. Your current also heads in that direction. Okay? And what is it that you're doing? Well, you're breaking this thing up into little sections here, okay? Little D3R primes. And you're figuring out the magnetic potential from each of these little sections here when it's got this J here, and then you're just integrating over it. Okay, so the same thing we've been doing. Notice, if the area of this thing, if the area of this thing is, let's say, little a, okay, so that's the area, I don't want to use big A because I'm using that already, of wire, then if the length of this thing is, say, ds, then I can write that my D3R is equal to A times ds. Okay, it's just the area of this thing times the thickness. And so that implies that my J times D3R is the same as J times A times ds, but J times A, that's just I. So I can write this also as mu naught over 4 pi integral I, where I is the vector of the current, ds over r. Okay, ds prime if you like. It's the vector at that point where that current is. Okay, so this is another nice way of writing this thing. Okay, and that's a whole lot easier because we've integrated currents along directions already. All right. So let's see an example. Okay. You got a long straight wire. Okay, long straight wire. So here's your long straight wire, and it's carrying a current in this direction. And you want to know up here, okay, what's that vector? Okay, what's the vector potential right there? Suppose you come up here some distance, let's say y from here, and this current is heading in the x direction. You want to know what's the magnetic vector potential from this long straight wire. Okay, how do I do it? Well, I can do it a couple of different ways. One, I know that, let me write, since I'm looking at just a current here, I want to use this form now. This should be A is equal to mu naught over 4 pi integral I ds over r, where r is the distance to each little segment. Here's my little ds, here's my r, which in this case would be square root x squared plus y squared. Okay, so it's not as scary as you might think. My ds in this case is equal to dx I hat. And so just writing these things out, I got mu naught I. Remember, I is constant here. Why? Because it's not branching off. There's no loops. Over 4 pi integral dx over square root x squared plus y squared. And then I would integrate over that limit. And this is I. So this tells me that only my A is some AX I hat only. And so I know that the vector field points in this direction. Okay? And so nothing to it. Okay, nothing to it. Now, I got to do this integral. And the integral turns out to be complicated. What's the limits? Well, here's where we got to be a little bit careful. Okay? I'm going to actually let this go from minus L to L and then kind of look at the limit as L gets big. Okay? Because actually if I plug in plus to minus infinity, this thing diverges logarithmically. Okay? And so it's kind of an issue. All right? So I need to do this integral. So my A sub x is going to be mu naught I over integral minus, well, let me just write it right now. Minus L to L dx over square root x squared plus y squared. Now, I think you can see, again, this is an even integral. The contribution from the left of the origin counts the same as the contribution from the right. So I can write this as mu naught I over 2 pi integral from 0 to L dx over square root x squared plus y squared. Okay. Now, you got to look up the integral, and it turns out to have an expression this way: x squared plus y squared plus x from 0 to L. All right? That's the integral. Okay, you can look it up. Now, let me just plug in these limits. And again, remembering that L is going to be a whole lot bigger than 1. Okay, it's a big number because this is a long wire. So this will be mu naught I over 2 pi natural log of square root, let's see here, L squared plus y squared plus L all over y, okay, which is pretty much the same. Since L is a whole lot bigger than y, we're going to assume, because again, it's a long wire and I'm imagining I'm not going too far away, this is pretty much mu naught I over 2 pi natural log of 2L over y. Okay? And so that's the answer. Now you say L blows up. Yeah, but it turns out not to make a difference. Okay? Why? Because you can always add to A some additional constant. Okay? You can always... Well, let me write it. Okay, so my A, what's the answer? Minus, where the heck did the minus come? You'll see. Natural log of y over 2L. I hat. I put in a minus because I like the y in the numerator more than the denominator. Okay? Now, this L here, doesn't this blow up? Yes, if you set L to infinity, yes, this causes problems. That's issues and so on. Okay? But remember, A isn't unique. You can always add to it an additional constant. Okay? Suppose you want to choose A equals 0 at some spot. Okay? At, say, y equals some distance, let's say r. Okay? Suppose, in other words, you've got your wire, which is traveling along here. You come out here some distance y, but you say, I want my A to be equal to 0 there. That's like choosing a voltage to be equal to 0 at some spot. Well, if you do this, okay, you can add to this. So you add to a constant, which doesn't change the A, because remember, you're taking the curl of this thing. Okay? What constant should you add to this? Well, I take A plus a constant, and I want this to be equal to 0 when y equals r. And so this should be equal to a constant minus mu naught I over 2 pi natural log of r over 2c. And so that's my constant. And when I add this constant to my A up here, okay, then I find that A should be equal to minus mu naught I over 2 pi natural log of y over r. And so everything's rescaled. The L doesn't show up anymore. Okay? I hat. Okay, that's the idea. So in other words, this L doesn't make a difference. And in fact, you're going to see why it doesn't make a difference in a minute anyway. And so that's my A. Right? Now, I want to check that this thing gives me the right magnetic field. Okay? But let's see another way of working out the same answer. Okay? The same answer or, equivalent answers. The whole idea is that if I can figure out voltages for this same sort of situation, for an electrical analog of this thing, then I can figure out what the A is. Let me show you what I mean. Remember, the electric case. Suppose you got a long charged wire. Okay, and so here's your long charged wire carrying a uniform charge. You might remember from Gauss's law that the electric field in that case was lambda over 2 pi epsilon naught times r, where lambda, let me call it y in this case just to make it sort of more explicit, where lambda was the charge divided by the length, okay? Which, if you like, is the charge density times the area of wire. Okay? So I'm just writing it this way. Okay, so this is my charge density. Charge per unit volume times the area of the wire. Okay, so again, lambda will be rho times A. So that's that. Suppose I want to know what the change in voltage is, okay, between 2 points from some spot here, let's say R, to another spot here, Y. Okay, what's my delta V? Well, hopefully you remember. Delta V is minus integral from R to Y of the electric field dr. Let's integrate that. The electric field in that case should be minus lambda over 2 pi epsilon naught natural log of y over r, which I can write as equal to, oh, I think my thing froze. Maybe not. Which I can write as equal to, using this, minus rho a over 2 pi epsilon naught natural log of y over r. Okay, so that's my difference in voltage. So my voltage is, just to write it, minus rho a over 2 pi epsilon naught natural log of y over r. Now remember, I can get from V to A by replacing 1 over epsilon naught, switches back and forth between mu naught, and my rho switches back and forth between J. And so notice, rho times times this little area is the same as J times the area, and that's my I. So I make these replacements. So this becomes A is equal to minus rho A is I over, mu naught, 2 pi natural log y over r. And I hope that's exactly the same thing as I had here. And yep, sure enough it is. Okay, then you just got to figure out the direction, because again, the direction is in the same direction as the current, and so this would be I hat. Okay, so you see that? So it's really not so bad. So you can figure out the expression in all kinds of nice cases. Okay, now let's check that this actually gives you the right field. Okay, which you can kind of see because you're going to be taking a derivative of this thing. Obviously, with respect to y, you're going to get something like mu naught I over 2 pi y. Okay, let's just check it. The magnetic field is the curl of A. Okay? And if my A, again, is minus mu naught I over 2 pi natural log of y over r, okay? For this spot up here, okay, if the current heads in this, actually I got to go back to here. In this case, if the current's heading in this direction, B should be pointing out of the board. So B should be some B K hat. Let's see if that's what we get. Now I'll remind you what this curl is. Again, you can think about it in terms of your determinants here. Okay, working it out, you get dAz dy minus day dz I hat plus, yes, I know minus, no, I'm switching the order inside. Dax dz minus daz dx j hat plus y dx minus dax dy k hat. Okay? Yes, I know that usually this is a minus, but I switched the order in here. Why? Because look at the order. Z, x, y, y, z, x. There's a nice cyclic permutation here. Okay? So, in this case, this is a x I hat. So we only have, in this case, we only have an x component. So that means this is 0. And this thing here is a x of y only. Okay? So this is 0. The only piece that we have left is this last piece. And so in this situation here, the entire curl breaks down to the only piece that's left, minus dax dy k hat, so the direction's right. And again, my ax was equal to minus mu naught I over 2 pi natural log of y over r, which is the same thing as minus mu naught I over 2 pi natural log of y minus natural log of r. And this is why the L doesn't make any difference. When I take a derivative, this is just a constant. And so the derivative of this gives me minus mu naught I over 2 pi r. Derivative of natural log is 1 over y k hat. And so this just becomes mu naught I over 2 pi y k hat. And that's the correct thing. Okay. Notice also, del dot A, dax dx plus day dy plus daz dz is equal to 0. Why? We only have an x component and it doesn't depend on x. So our Coulomb gauge condition is satisfied. Okay, so that's nice. Right? One more nice example. Okay, then I think we'll kind of leave it there with maybe a couple words about something else. How about a solenoid? Okay, remember in this case the magnetic field of a solenoid was very simple. Okay, B inside, and remember what a solenoid was. It was this loop of wire here. And if I had n turns and length, let's say L, then I define this n was n over L, n turns per unit length. And if the wire is carrying a current which flips around, I here, this is equal to mu naught n times I. Okay? And suppose that it's in the I direction. Okay? That was the field inside. Okay? B outside was equal to 0. Okay. So from that I want to figure out, well, what's the vector potential? Okay? The vector potential, remember, points in the same direction as the current, so it should spin around. How can we figure that out? Well, here's something very interesting. I can go back and do the integral and so on. Okay, it's some work, but it's not undoable. But here's another interesting thing. Remember, my B is equal to del cross A. Let's suppose that I integrate the flux of B. Okay, so in other words, I work out integral B dot dA. Isn't this 0? No, it's through an open surface. It's not through a closed bubble. Okay, in other words, I take a little surface here and ask, well, how much B is passing through that surface? Okay. What's this equal to? Well, because B is del cross A, this is integral. Let me use a little a here. Okay, a little a for my area. Why? Because I've already got an A. Dot dA. Okay, so the little a here represents my little area. Okay. But remember, by Stokes' theorem, okay, go way back here to Stokes' theorem, wherever it is. Right here. I can write this thing here as a surface, as a line integral. So this is the same as equal to integral A dot ds, where ds is the line loop around that area. So in other words, the integral of the flux of B, dA, is the same as the integral of the line integral of A around that area. Okay, so let me rewrite this, okay, because this is handy. So suppose that you've got some, let me draw it. You got some loop here, and you got a B passing through it. Okay? This means that you're going to have an A that circles around it. Okay? And so this theorem here says that integral of B dot dA, okay, some little area through this thing here, is equal to integral of A dot ds integrated on the loop that surrounds that area. So this is very nice. Okay? Why? Because in the case of the solenoid, now we can work this thing out a whole lot faster, a whole lot easier. Okay? A nice tricky way of doing it. Okay? For the solenoid, okay, if I take an Amperian loop, notice this is very much like Ampere's law. If I take an Amperian loop of a circle of radius say R, then A is constant on that loop. Why? Well, if I imagine my solenoid, the current keeps going around, and it's very, very symmetric, and A points in the same direction as that thing. So A should also cycle around. All right? And because of that, because I can twist and turn this solenoid however I like and it still looks the same, that means that it's got symmetry, and that means that A should also look the same. So A should be constant on a loop around this solenoid. Okay? So this tells you what kind of loop I should take. Okay? So here's the thing. Okay? Here's my solenoid, okay? And this stretches down here. I want to figure out what's A inside and outside. Okay? Let me start off inside. Okay? So here's the idea. I go out here some distance r from the center. Okay, and this thing has got some radius, let's say big R. And I draw my little Amperian loop, okay, of radius r. And again, I know A is constant on this loop. Okay? So that means that if I work out integral A dot ds, for all the reasons we've talked about before, this should just be A times 2 pi r. Okay? Also, I know that A travels around this, okay? Because if the current is moving in this direction, then that means that A also travels in that direction. All right. So this should also be equal to integral B dot dA. Now, what's B? Well, inside. So this should be equal to integral B inside times my D area. Well, inside, B inside, was equal to mu naught N times I. Okay? And so that was just a nice constant. And so if this is constant, this becomes B inside times the area of that loop. And so that should be equal to B inside times pi r squared. Okay, it's just the area of that loop. Okay, nothing to it. And so I just plug in B inside as mu naught Ni times pi r squared. And I set this equal to that. And so I find that A inside is equal to, let's see here, mu naught Ni over 2 times r. Okay? And if you want to throw in a direction, remember it's spinning around, so you get this little phi hat thing. Okay, see, nothing to it. Now I just have to do outside. All right, so let me redraw it. Okay, so again, here's this. Here's my solenoid. Now I want to come outside out here. So again, this is radius r, but I come out here to radius big R, and I draw my same loop. All right? And so I do the same thing. Again, A's got to be constant. And so that tells me that integral A dot ds should just be the same A times 2 pi r. Okay? And so this is A outside. And this should also be equal to integral B outside, well, B dot dA. Now what's that? Now here's the thing. B outside is equal to 0. So does that mean that I just set this equal to outside? No, I don't just set this equal to 0, because there's still some amount of current passing through there. There's still some amount of flux passing through there. But it stops here. It's only the stuff inside. So this is only integral B inside, which, just to remind you, was mu naught N times I, times integral dA, where this is the area inside. Okay? Out here, there's no contribution. There's no flux from the magnetic field. The flux stops here. And so this becomes mu naught Ni times pi big R squared, because that's the end of the road for the magnetic flux. Okay? So it's not little r squared, it's big R squared, because there's no magnetic field outside of the solenoid. And so setting these things equal to each other gives you A outside is equal to mu naught Ni over 2 r squared. And again, if you want a direction, phi hat. Okay, so we got it. Notice A inside at r equals A outside at r. Nothing to it. Okay, nothing to it. Now, we really should check that we get the right B inside. Okay, inside and outside. Okay. In order to do that, I need to take the curl. And in this case, it's better to do it in cylindrical coordinates. Cylindrical coordinates where you take r, which is this distance, phi, which is this angle, and then z. Okay, so r, phi, and z for your coordinate system. And so your a here is expressed as some a r hat plus a phi hat plus a z k hat, or z hat, whatever you want to call it. Okay? For us, we only have this phi component because we know it's spinning around. Okay? In this case, you look up your expression for the cylindrical coordinate curl on that useful sheet, and it's a big mess, but it turns out that because you only have this situation here, okay, where this thing depends on r, okay, so in other words, you have a phi of r phi hat. Because in this situation you have it, this whole thing reduces down to 1 over r. And again, you look this up. 1 over r ddr of r times a phi k hat. Okay? Where I'm calling this direction k hat. This is the z direction now. Okay? So b here, if you want to take b in, this will be a k hat. Okay, just to be consistent with everything. All right. So let's check it. Inside. Okay. I got 1 over r ddr of r times my a phi inside, which is right here, mu naught ni over 2 times r k hat, and this is going to be equal to mu naught ni k hat. And so that's my b inside. Okay, it works. You're going to get an r squared. When you take the derivative, you get 2r, cancels the 2, and cancels the r in the denominator here. Whoops. Here, and so you're okay. How about outside? Okay. Well, then I got 1 over r ddr of r times mu naught ni r squared over 2r k hat. Notice I got an r here and r here. Nothing. This is a constant now. This is equal to 0. And so b outside equals 0. Just as expected. Okay? So everything is consistent. All right? And so it's very, very nice to sort of think in terms of these vector potentials and so on. It's a very simple sort of thing once you get the hang of it. And again, the nice thing is that we've done all kinds of work on this when we worked out the voltage. Okay, so if you know the voltage, you can figure out what the vector potential is in the same sort of case just by making these substitutions. Okay? And so again, you don't have to redo everything. Okay, so the vector potential is not a very, very complicated sort of thing. Okay, sometimes the math gets a little involved because you're taking curls and so on, but okay, it's really not so bad. Right? So I hope you spend a little bit of time looking at this. Okay? And certainly there's an interesting discussion that I just won't take the time to do now just because it's running late as usual, about the reality of this thing, okay? And I'll just sort of mention the idea a little bit, okay? We've got that because the curl in statics, okay, the curl of E is equal to 0, which implies that E is minus the gradient of the voltage. And also the divergence of B is equal to 0. That's not always true. B is equal to del cross A, okay? So, but when you write down the forces, for instance, you write down Q of E plus V cross B. And so in some sense, the fields are kind of the real things. And then these voltages are kind of these mathematical tools to make things a little nicer, make things a little easier. Okay? And so once you've got V and once you've got A, then you just do some derivatives and you get the electric and magnetic fields. Okay? But the question is, are these things real? Okay? Real in the sense that they really give you something you couldn't get from the electric and magnetic fields alone. Okay? And the answer is, if you're just dealing with classical physics, regular old electromagnetism, stuff that was known up to about 1900 or so, then no, they're just sort of nice mathematical tools. Okay? However, in quantum mechanics, then A and V actually do take on a reality. Because there are certain experiments, okay, one of them is called the Aronoff-Bohm experiment, which shows that no, A actually makes a difference. That you can have a situation in which, for instance, you got a solenoid, and you look at how electrons move around that solenoid, where the magnetic field is completely contained inside of here. Okay. So B is completely inside, B outside is 0. And you move electrons around this solenoid, and you find that they're affected, even though they're moving through a region where there's no magnetic field. There's no magnetic field, but there is a vector potential. We just worked it out. It's right here. Here. And so there's a vector potential. So it must be that the vector potential is a real thing, which is really affecting these electrons. And there's a very good discussion of it in the Feynman lectures. And so if you're interested in those things, I refer you there. I don't want to take the time because this is not a class on quantum mechanics. That's 103, and there's more discussion about this idea in there. But no, it does turn out V and A are real. And by real, I mean they're as real as the electric and magnetic fields themselves. And in fact, in the more sophisticated things of quantum field theory and so on, it's the A's and the V's that we care about, not the E's and the B's. Okay? And so these things are very much worth thinking about. Okay? And so this finishes off this part of magnetism. Again, the next lecture, I'm hoping to have a lecture on magnetic materials, okay? The magnetism of matter, which gets into H's and M's and some interesting things, in much the same way that I talked about the electric fields in matters, with those D's and P's and so on. I want to have that lecture. But again, that's sort of a special lecture in the sense that you won't be tested on anything from it. However, the lecture after that, then we get into the ideas of time dependence, okay, when we're not going to throw away all those derivatives, and we'll see a very deep, very interesting relationship between the electric and magnetic fields. Okay, so that's 2 lectures from now. All right, see you then.